Anytime.
All right, bye.
Sure, yeah. I don't think the camp's going on anymore. I haven't heard them all week, so it must be over. How's the homework going?
It was decent. It takes a long time, like you said. And I kind of just like did it as like I figured out like how to do all of them.
Mhm.
And then I would just like by the time I took the quiz and stuff, especially, I just like looked at the equation. I did all of the things like in order how I did it,
Yeah.
and then just went through there. They put in like different orders every time,
Okay,
but it's just
Cindy.
yeah. But once you get the concept of it, it's not too bad.
I'm a little nervous about this one.
Yeah, I did struggle more than I have on the other ones. For
Well,
sure.
I'm talking about the one we're gonna talk about today.
Oh, okay.
I think it's gonna be the hardest homework of the semester. There's some real, so there's a good chance that I have to go slower. So bonus. I'm already dreading. I tried to highlight those. You one each time. The problem is there's maybe 4 or 5 different types of problems,
Yeah,
and each one is kind of difficult. I like the more algebraic difficult.
yeah,
I don't mind that. I like those. The thing I don't like is like when it has like 12 parts, because that just means this problem's gonna take forever.
mhm,
Even if because each problem you have to read, understand, think about what am I doing, like all that. It's okay. Cassandra, welcome to class. All you know. So it's 1 o'clock. Attendance has been incredibly low for this class. I'm not sure why, but so grades, not present coverage excluded. So that's lining up perfectly. Emails are up, grades are down. So if you're watching the video, I would try to make it a point to come to class, even if you can't physically come to class. I think you'll get something out of it because I've noticed those that do have higher grade than those that do not, which are a lot of zeros. So you should be doing better than that. Okay. I think that this week 6 is particularly difficult. I had a personally rough week, and that always, of course, affects your ability to think. My son has been sick, and I've been sleeping on this floor for the past like 2 weeks. So I'm just like, it's like I have a newborn, even though it's 3.5. So I've just been fried. But you know how it is. I mean, you guys have lives too, so you know how it is. But I think this one's just kind of rough. So what I am anticipating on doing is if I can't get through all of the types of problems, then I will post some bonus videos on particularly difficult problems, okay? So that way you at least have, even if I can't get it all done live in class, you'll have something. You'll have my lecture notes posted as well. And if I can come up with any extra material to kind of speed things up, I think that would be good. One thing I'll go ahead and say is don't hesitate to use a scientific calculator on this homework, okay? I'm gonna show you a couple different ones. I used a few different ones during my doing the homework, so definitely utilize the calculator. Desmos is incredibly helpful, especially when you're doing the homework. That can speed things up quite a bit because it can do all the arithmetic, quickly, and that can really help. Because I always end up making arithmetic mistakes. All right, what are we learning today? This is a big warning. What are we actually learning? The problem with this week is that we're learning about 5 different things all at once, and it's really coming to a head. So we're really at the pinnacle of the derivative. So this week is really kind of, this is everything you've learned about the derivative all at once. So we have really hard derivatives that we're going to take. That's a portion. We're going to utilize the derivative with applications, specifically profit, because this is often taught as a business class. So there's a lot of revenue, profit, costs that we are working with. There are some geometric and volume 2D, 3D optimization problems that we're going to look at as well. Those are similar to the cost and revenue functions. So there's a lot going on at once, and it always takes more time. So I wish we had about 3 weeks to do this, and we have 1, and I have 3 hours to do it. So let's do it, and I'll try to explain. I've already posted what I think would be a gold tier math video. It's the MIT lecture that corresponds with maximizing the function. Totally extra credit, or not extra credit, just extra if you want it. If you want to see how this is really taught, that's a tremendous video, and it's the same video I watched when I learned it. So it's old, but it's good. So if you want to learn like the pros, that's a good video. So that'll be posted in announcements. Totally extra if you think you need it. Also, the good thing about our homework is that I think 99% of the problems have help. So at least you have something you can look at. You have an example for every problem, almost every problem. Okay. Anyway, so what are we learning? So we're going to maximize. We've already talked about that. How do you maximize? How do you minimize? So to max and min, what did we do? We found df, dx, and we set it equal to 0. Why did we do that? Because when the derivative is 0, think about a parabola. There's something that's changing. If the derivative is 0, so if it's 0 at that point, what's going on? There's some kind of change. That's the maximum. So this is an idea of a maximum. So that's really, really important. And there's all kinds of applications like rocket science, like high level finance, geometric and engineering and manufacturing examples. I mean, there's almost infinite examples. Okay? This is just one of them. Number 1, of all numbers that add to 48, find a pair that has a maximum product that is maximize the objective function q equals xy subject to the constraints of x plus y equal 48. Okay. So we have 2 numbers that add to 48, and we want to maximize the product. We want to maximize the product. How can you maximize the product? Well, this is single variable calculus, so let's try to get it down to a single variable, right? So I'm going to rewrite this as y equals 4 minus x. Why am I doing that? Because I only know how to take derivatives of 1 variable, not 2. So that's what I'm going to do. So then q becomes x 4 minus x. Okay, all I did was sub it in. I just subbed it in. Haven't done anything fancy yet. Then we have 4x minus x squared, and that's cubed. So I haven't done no calculus yet. The only thing I've done so far is subbed in, okay? Now, we want to maximize. How do you maximize a function? Let's find dq, dx, and set it to 0. And this is a upside down parabola, so it would have a maximum. Okay, so dq sounds good right now, by the way. Dq dx is 4 minus 2x. All right, I'm liking those numbers. I'll set that equal to 0. 4 minus 2x equals 0. So 4 equals 2x, x equals 2. Now, let's plug that in. Y equals 4 minus 2. There you go. 2. So Q equals 4. Why is it 4? Sorry about that. I did put it-
48.
Which one is it?
I think it's supposed to be 48 instead of 4.
Oh,
I tried to look
yeah. Where did I?
all the way.
Where did I? All the way up here, I messed up. Thank you, thank you, thank you.
Sorry, I should have let you know.
Oh no, I appreciate you letting me know. I think I'm gonna have to erase some things. Man, that's all it takes, is on the first one. Okay, that should have been 48, not 48, 48. 48 minus 2 is now, probably should just rewrite. Eight. 48. 48. 48. 48 divided by 2. I think still, yeah. X equals 24. Coincidentally, that's the correct answer. Y equals 48 minus X. 48 minus 24. 24. Sorry about that. Slip of the pen. Okay, so that was the idea. What did we do? We maximized dq dx, set it equal to 0. Solve for x. Once you do that, easy stuff. But don't forget the 8, because then it's wrong. All right, I think number 2 is similar. Let's take a look at it. Minimize the function q equals 5x squared plus 3/8y squared, where x plus y equals 8. So again, I'm going to solve for y. Y equals 8 minus x. So if that's true, then q equals 5x squared plus 3, 8 minus x squared. Now I should probably expand. Before I get into anything else. And we have 5x² plus 3x², which is 8x² minus 48x plus 192. So this is a parabola of this type. Okay, so it won't have a maximum, but it will have a minimum. So we need to find dq dx. 16x minus 48. We want to set that equal to 0 because we want to find this minimum. All right. If I do that, 16x equals 48. Let's just which is 3. So x equals 3. If x equals 3, we can go back up here, plug it in. Y equals 8 minus 3, which is 5. What are we learning? Okay, we're learning that, so we're kind of on the edge here. We're still taking derivatives, we're finding the min and the max, but what's really going on is that we're starting to deal with two variables. So we really are kind of on the borders of what this subject can take us. So now I'm solving for the other variable, plugging it in so I still get a single variable. So we kind of have to do a little algebra trick to get it going. But the idea is still, if you take the derivative and you set it equal to 0, that's going to give you the maximum. Hopefully that makes sense. That's 3. Was it 3? Yeah. A lifeguard needs a rope off a rectangular swimming area in front of Long Lake Beach. Using 2,500 yard of rope and floats, what dimensions of the rectangle maximize the area? What is the maximum area? Note that the shoreline is one side of a rectangle. Okay, well, we know what the area of a rectangle is. It's length times width. They're saying that we have 2,500 yards of rope. What are the dimensions of the rectangle that maximize the area? So we want to maximize area. Hopefully dA dx, set it equal to 0, solve for x. That's my game plan. I hope you've studied perimeter once before, but I believe this is the perimeter. So the perimeter is 2,500. That's the length of the rope. Okay. So what is that? That's this length plus this length plus this length plus this length. Perimeter equals 2 times length plus 2 times width. So that means we can turn that into the area in terms of a single variable. Okay. So the area is then 2,500 x minus 2x squared. If you distribute. Now from there, we have to maximize. So we want to, again, we want to find dA over dx, set that equal to 0. And we have an upside down parabola. So that means we will have a maximum. Okay, so what is dA dx? That's 2,500 minus 4x. Set that equal to 0, that's going to give it to you. So 2,500 equals 4x. Okay. So what's 2,500 divided by 4? X equals 625. So we have the short side, you could call that the width, is 625. So then you're just solving what is the other side. 100 is 2, let's call it L, plus 2 times 625, solve for L. That's for my numbers, 12. Then we have maximum length, maximum width. Okay. Then we can just multiply them. That's the product. Area is the product of these two numbers. But the strange issue is we have like elementary geometry all of a sudden popping up in our question. We have calculus going on. We have two variables going on. So things are getting complicated all at once. That's the idea. That's the idea. So the idea is that even if you have two variables, if they're related to each other, you can solve for one variable, plugging it into the equation, the derivative of that equation, set it equal to 0, and that will tell you the maximum. Minimum, so you can determine what of interest is that to you. All right, normally I would skip to 5, but I want to do problem 4 just because it's a classic problem. I should at least talk about it because I'm worried it'll show up on the final, because this is one of those quintessential problems, at least a version of it, and that is to find the dimensions of an open box. So we have some open box and we're going to try to find the dimensions of it, the volume. And you guys know the volume. Length times width times height. That's the volume of a box. We're going to try to find the maximum of this. All right, well, I can find the minimum of it too, but what's that going to be? That's going to be dB over dx equal to 0. dV over dx equals 0, solve for x. That's my game plan. Now I have to find the dimensions of that. All right, they say that the maximum volume that can be made from a sheet of cardboard is 19 inches by 11 inches from the corners of the folding up boxes. Then the volume, find the volume. Okay, so what is the volume? 19 inches. I can't draw this to save my life, but that's kind of a picture. If we like flattened out the Amazon box, you're trying to find, okay, what is the volume of this box? So you know it's length times width times height. You have 19 and 11. So you're just gonna have x 11 minus 2x and 19 minus 2x. Where does the 2x come from? You have x here, x here, x here, x here. Okay. So x is there. You have to deal with. But once we have this, now we can take the derivative of it. How I did it was I distributed, then it's just a power function, and I can just take the derivative of it that way. So that's what I'm going to do here. So x will be little time. That's 8, 209 minus 22x minus 38x plus 4x squared. 209x minus 8 minus 22 plus 22. 16. 2x plus 4x squared. Okay, take the derivative of this. Let's see, this should be an x squared and this should be an x cubed. Yeah. 209 minus 120x plus 12x squared. And we want to set this equal to 0. Okay. If you like, what you can do is you can graph this and then find where the x-intercept is. You could plug it in the quadratic formula, or you could, oh, there's lots of different ways, but you found that x equals 2.25. And then from there, it's fairly easy to see what the other dimensions. This was length, this was width. Pretty easy to figure that out. Okay. But here you can just use the quad, or you can use a calculator, or just solve the quadratic equation. But you have your length. So I saved a picture. I'll post that here. That's the idea. Okay, that's the idea. But really, what are we learning? If you take the first derivative, set it equal to 0, that's going to give you a maximum or minimum. Okay. Once you do that, then you can plug in length equals 11 minus 2x, width equals 19 minus 2x. Solve. Now, 25F. Let's do problem 5. This, I don't know which one it will be, but something like this is going to be, there's definitely going to be revenue, profit, and cost on the final exam. And there's a lot of it on this homework. So the good thing is you will be able to review that while you're doing it. We've talked about it before, but we're going to talk about it a lot more. So what is profit? Okay, let's think about it in the elementary school world. We have a lemonade stand, and we had to buy supplies, or mom and dad had to buy supplies to make our lemonade stand. Maybe the stand costs a certain amount, maybe the supplies, the lemons, the pitchers, the water, the sugar, all of that. So we have costs in there, right? Revenue is the money coming in. Profit must be the difference. So whatever came in minus whatever we paid, that in turn is our profit. Okay, so that's in the basic sense, but these are quadratic, so that's not elementary school anymore. And to find the maximum is certainly not. But P of X equals R of X minus C of X, right? It's just money coming in minus the money going out. That's your profit. We want to maximize profit. All right, so let's do that. So the profit equals the revenue minus the cost. 50x minus 0.5x squared minus, don't forget your parentheses, 5x minus 15. 50x minus 0.5x squared minus 5x minus 15. That looks like that would be negative 0.5x squared plus 45x minus 15. And that's my P of X, which is an upside down parabola. Okay. That means there's a maximum. So to max P, take dP, dx, set it equal to 0, solve for x. And a single variable equation, I can take the derivative of it. And from there, I should be able to find the maximum, because it is, after all, an upside down parabola. So that would be -1 x plus 45 equals 0. So it looks like x equals 45. All right, if x equals 45, what is the profit? What is the profit? This is where it occurs. How much do I actually get? So 45 don't like the way. Made a single variable equation, took the derivative, set that derivative equal to 0, solved for x. This is where it occurs. Now I plug that x into the original function, and that tells me the amount. That's pretty much the same thing we did last week, except we had to come up with the equation ourselves. And this is technically an application problem, because it's, revenue and cost. There's a high probability that something like this will show up on the final, because that's one of the core things we're learning about. It's revenue, cost there. Any questions about that one? I mean, we'll see some more later, but that's kind of the good one. At least keep a hold of this, okay? You got to remember profit. Of course, in your homework, it'll just show you an example. Let's look at 7. So a clothing firm determines to order to sell X suits at the price per suit must be P equals 110 minus 0.75 X. It also determines that the total cost of producing X suits is given by this cost function. Find the revenue function, find the total profit, and then how many suits, what's the maximum profit, what's the price per suit. Okay. How do you find the revenue function if we have the P? If we have the P, which is the demand. How do you find it? Well, that's one of those equations. So R of X equals X times T. We're gonna need that part for our second part of the homework too. I'll remind you when we get there, but we need this as well. So it's XP. Okay, what's XP? For my numbers, that's just X times the line that they gave me. So I just need to put an X there, and that's squared. So there's my R of X. All right, find the total profit. Find P of X. What is P of X? Profit is revenue minus cost. Revenue minus cost. Think of our lemonade stand. Okay, so we have revenue, and they gave me the cost function, so I just need to do it. So I found the revenue equation. And they gave me the cost function. Don't forget your parentheses for those tricky signs there. We'll make a sign error. Now I just need to do some simplifying and should be good to go. Okay. So that for the X squared, I have negative 0.75 minus 0.5. That's like 75 cents and $1.50 is $1.25. x squared. We have 110x for my numbers, and then minus 2000. That's just p of x. I haven't taken the derivative of it yet. Just finding p of x. Now, how many suits must the company produce and sell to maximize profit? How do you maximize profit? dp dx equals 0. And this is an upside down parabola, so that would do it for us. So my derivative would be negative. What are they doing? Don't they know I'm trying to do calculus in my head? Some kind of construction. I want to set that equal to 0. 10 divided by 2, 5, 44. And 44 suits. What is the maximum profit? So we plug that in. However many suits we just got, we plug it into our profit function. What is our price per unit at this amount sold? P, maybe I'll do different color because it's pretty messy. P equals 110 times 44. For my numbers, I got $77. So what do we do? You're somehow, by some magic, they know the cost function and they know the demand function. Okay. From there, we can find the revenue, the profit, took the derivative of the profit, set it equal to 0, found the x. Okay, that's how many suits. Found what the maximum profit is. Okay, so if that's the maximum profit, let's go all the way back to the beginning and find what price we should set our suits at. I could imagine every corporation ever would be interested in something like this. The magic comes from, where does that cost function come from? Where does the price function come from? That's the magic, but from there, we can do it. How's it going?
I'm really confused about, okay, are you just taking? Cause P equals 110.
This was given to me,
Okay,
and then I solved for how many suits, so what would the price be?
yeah, I see it now. For some reason, thought there was.
Online folks, how are we doing? Okay. Was going to do 11. I think 12 would be better. So I'm going to 12. I'm going to 12 because it's a whole nother type of problem. So most of those are just similar. But this is kind of a whole nother thing. Doesn't mean that this is extra hard, it just means it's extra different. So we have y equals 2x cubed. They're saying x equals 5 and delta x equals 0.01. We want to find delta y given x and delta x. Then we're going to find dy equals f prime of x dx. Then we'll find dy for x and delta x. All right, what are they on about this? So it's kind of one of those things. They're taking what we've already learned, they're building it up. I don't know how great of a job they do of explaining why they're doing it, but this is a pretty good problem. I just wish they did a better job of explaining why we're doing this. What we're doing is we're actually kind of branching what we've learned with the derivative, and we're going to next week where we're going to learn about the antiderivative. So we're not doing the antiderivative, but we're really taking apart the derivative, examining it, and that's going to be extremely helpful to us next week when we take the antiderivative, which is the ultimate thing we learn, okay, in this class. So let's do it, and then we'll see it's not that bad. And then hopefully I can explain why it is that we're doing this. Let me move that down. So the first thing is we want to find delta y. Okay. So delta y equals numbers f of x plus delta x minus f of x. That should look kind of similar to something we've looked at before. Recall the definition of I mean, you don't have to, but I'm just trying to piece it together of why we're doing this. F of x plus h minus f of x over h, where h goes to 0. So notice that numerator there, x plus h, you could also think of it as the limit as delta x goes to 0, f of x plus delta x minus f of x over delta x. That's the idea. So it is just a different version of the derivative we've already learned. Let's do it for these numbers. I have 2 plus x plus delta x cubed minus 2x cubed. Okay, but they give me actual numbers. Okay, so 2, 5 plus 0.01 cubed minus 2, 5 cubed. So they gave me x, they gave me delta x. Okay, so then I can find delta y by using this formula. Okay. So I got 1.5030 when I plugged that into my calculator. That's all I did, just plugged in my calculator. That part.
I'm just.
No, I suck. So this is delta y. I claim that this is really just the same thing we learned before, maybe in week 1 or week 2. It's just extending it just a little bit. Okay, so they're giving me delta x. They're giving me the x. I just evaluate it at a number. Fair enough. Then this other part, they say, okay, find dy equals f prime of x dx. This is part B. Where is this coming from? This is coming from the idea of dy dx equals f prime of x, which we have used ever since we learned the derivative. We just use that interchangeably. Okay, we use those symbols interchangeably all the time. It's now that we're saying, well, actually, this could be thought of as a ratio. As the change of, I mean, that's how we define it. It's like a slope at any given point. Think of this as a ratio. This is dy f prime of x dx. So I just multiply both sides by dx. I get dy equals f prime of x times dx. Doesn't seem like that would be that big a deal. And it won't during this homework, but it actually is a tremendously big deal. So let's do it. So we want f prime of x. What is f prime of x? So they gave me f of x equals 2x cubed. So what's f prime of x? Well, for me, it would be 6x squared. So I just take the derivative normal over there. Just take it normal. Now, that's 6x squared times dx. And that's what they wanted. So I just took the derivative as normal. We've seen dy dx equals f prime of x. That's how we defined it. We've been messing with that for a long time. That's no problem. But then all of a sudden, I'm multiplying both sides by a differential. Never done that before. So that's pretty weird. Now they say, okay, solve for dy given these numbers. So that's what I'm going to do. I'm going to plug in the numbers they gave me. And x equals 5. That's going to be squared. The dx is 1/100th. (25 times 6 divided by 100 for my numbers, 5. It seems like just a weird algebra problem or, calculus, I suppose. But what's really going on here is that the homework is starting to bridge the gap between the derivative and then there's these differentials. And it turns out that this part is going to be a really big deal. Dy equals f prime of dx. That's going to be huge. That's going to be huge. Next week, we'll see why that's so important. Okay. If you take calculus 2, you'll spend the whole semester finding out why that's important. So it's really important. Okay. It's going to lead us towards the antiderivative. The fact that we can examine these differentials independently. Very important. Okay, I'm going to show 13. I think it's just a different version of this problem. I'm going to show this one just to kind of hammer home what's going on here. So I'm given a different problem. This time it's just a line. Okay, so it should be easier. I have f of x equals 7x minus 2. They're saying for me x equals 5 and delta x equals 4. So let's find delta y. So delta y is defined to be f of x plus delta x minus f of x. Okay. So my f of x plus delta x would be 7x plus delta x minus 2 minus 7x minus 2. Don't forget your parentheses, like my algebra students would do that. And since we're just dealing with numbers, we could plug them in right now. So that becomes 7, 5 plus 4 minus 2 minus 7 times 5 minus 2. And I got 28 when I plug that So since we're just evaluating the numbers, we can just plug those in now. Okay, so there's delta y. We're going to hold on to this equation here. It's important. For the next part, we have dy equals f prime of x dx. We just talked about why that must be true. Okay, so what is my function? Mine is 7x minus 2. So f prime of x is just 7. Then dy equals 7 dx. Dy equals 7 times the delta x they gave me, which is 4. 7 times 4 is 28. And we see these are the same. So this thinking of, I remember when I really understood this, it almost blew my mind open. The fact that you could move differentials like that, shocking to you. I mean, when you're first learning it, you're just kind of, you're just going along. I don't want to say copy, but that's kind of what we do. Like if you learn music, like at first you just learn someone else's music, and then eventually you go on your own. But when you really understand something, you go, oh my God, that's amazing. The fact that you can break up these differentials. And this equation here is going to allow us to come up with the antiderivative, okay? And that's gonna be monumental. As a matter of fact, it gives us the fundamental theorem of calculus. So extremely important. That was 13, and got about much time. What'd you say?
I was like, you have 2 hours left.
2 hours, honestly. Let me get the good ones. There's 13. What, 17? This one, that wasn't too bad. Just, it gives you the profit function. That's pretty straightforward. So because it has fallen example, I'm not gonna go over that because there's not too much calculus. You can follow the instructions. That's not too bad. Let me peek at 19. That's also not that bad. You're just gonna take the derivative and it's just power, plug in there. So I think that's okay. A little time consuming, but those are okay because they're just, you can follow the instructions. So I think those would be okay. 20. That should also be okay. Let's take a look at this one. So for this one, we're given a equation. It tells us that chemotherapy dosage depends on the patient's surface area. So this is one, get out your graphing calculator for this one. I'm going to use my graphing calculator for this. Okay, so we're told that according to this model, that's the surface area where H is the patient's height in centimeters, W is the height in kilograms, S is the approximation of his or her surface area in square meters. This particular patient at least for my numbers, is 170 centimeters, and I have 70 kilograms. Use the differential to estimate how much her surface area changes after her weight decreases by 1 kilogram. Okay, so I think we need to go dy equals f prime of x dx. That's what I'm reading it, okay? And what we've just learned, that would be. So it's pretty ugly looking, but in truth, I don't think we're gonna have to, as long as we just use a calculator, we'll be okay. Now, what are we taking the derivative of? dH or dW? That's something we have to worry about. Differential using change in her weight. So that to me sounds like we're doing dW. So I think we need to find ds dW. So let's find it. And then that would be my S prime. So let's find it. That means that this right here is going to come down. It's going to come down, right? So we need to leave H alone. It's going to, the exponent on the W will come down. So I'm just going to copy this down. This, I think, is the same for all of our numbers. I think the model is the same. Okay. Then I still have H there. Still have that exponent. I have W, and then it's going to be that exponent minus 1. Okay. 0.51456 minus 1. And I get negative 0.48544. So that's S prime for this function. This is S prime. This patient's weight, I was given the weight, I was given their height. Okay, so I could plug that in. I have a feeling that changes depending on our version of the problem. So I'm guessing you have a different height. I don't know, but I think you do. Maybe I'll just multiply that now. 0.02235 times 0.51456. Zero, 0.0046. My patient's height, I'll write it in red so you can see if you look back where I plugged it in. Okay. My patient's weight is 70. And then I think we'll have the same exponent. So that's S prime plugging in the numbers, right? But then I have to multiply it by dx. What is dx? For mine, it was decreased by 1 kilogram. Kelsey, is that the same for yours at the very end?
Yeah.
Is it 1 kilogram?
Mhm.
Decreases. So I think I'm going to write it in 1 just in case me and Kelsey just coincidentally have minus 1. But the differential is decreasing by 1. So I'm going to plug in negative 1. So the red, or where I'm plugging in the numbers, everything else should be the same for everybody. Okay. Now, the fun begins of plugging in your calculator, or you can use an online calculator. That'll give you your dy. Okay. From there, I was And I personally used, because, it's a lot to plug in. I use Desmos, so I'm gonna use this once again, to promote Desmos. I highly suggest it when you're doing your homework. You have a graphing calculator here, and you can also use a scientific calculator there. So we can plug that in. Easy stuff, right? So it's 0.0115. 0.4246. 7. Round, however, we're spelled round. I don't know why it's subscript. There we go. Kind of a mess on screen, but there it is. So I use Desmos to plug it in. I found that to be a lot easier than if that's just computing. That's not that big a deal. All right, kind of interesting. So that's the idea. That is part A. What did we talk about? Really, this is the applications. And with the applications, we're taking derivatives. Sometimes it's more than one variable. Set the derivative equal to 0, then you're able to maximize or minimize. So optimization is what we're talking about. Then we're also talking about the fact that you can break up these differentials. Think of them that way is quite important to us, right? So that isn't so bad. There's some problems that are just a little tedious. I think are fine as long as you're comfortable with reading the instructions. There isn't that much calculus to be done. So some of them are a little tedious, but not too bad. I think it'll be, for the most part, this will be the easier homework. I hope so anyway. All right, so I'm gonna take a break, come back. When we come back, we'll do part B. Part B is kind of a hard one. We might even have to take a break again during B, so I might have 2 breaks. All right, so 10 minutes, come back, and then we will talk about B, and B has all kinds of things. Okay, I'm back. So the harder homework is part B, and it's, I think, maybe the hardest homework of the semester. So I'm gonna spend more time on it, and I really wanna do some of the hard problems. And there are some hard problems. One thing that might be of interest to you, it's not a giant interest of me, is I don't know if you're a business major, if you're going to be, I will let you determine how interesting it is to you. If you are going to go into business, finance, that type of thing, I would urge you to read section 3.7 in the book for business majors, okay? I'm not a business major, right? I'm a math guy, so I'm more interested in the math and not necessarily the application, but I can talk about it as well as anybody. This has to do with elasticity of demand. And I would imagine if you're taking this course to go into your business courses, you're gonna go way more in depth of where this would come in, where this is going to apply. To me, it's an application of derivatives. Anyway, so the book takes the time to talk about elasticity of demand. So profit, demand, revenue, cost, supply, that type of thing. A demand function Q equals D of X relates to the quantity Q of units purchased to the price X in dollars per unit, and usually decreasing function. Retailers and manufacturers often need to know how small increase in price will affect demand and total revenue. A small increase in price may result in a relatively small drop in demand, but higher revenue, so on and so on and so on. So if you're interested in this, or not interested, but if you need to know it, I urge you to go through this. Okay, what I need, they go through a nice derivation of how this works. Really, the only thing I need is the definition. So there's the definition of elasticity of demand and the given function, price X. So I just need that formula. Okay? If you're going into business, again, I urge you to read it, internalize it, maybe watch some YouTube videos about it. But I just need this formula of elasticity, which is E of X equals negative X times the derivative of the demand function divided by the demand function. That's a definition of elasticity, and I need that for my problems. Okay? But really, it's just an application. All right. So that's in section 3.7, and you can find that by just simply clicking Get More Help, go to textbook, and I'll take you right there. So let's actually do it. For question 1, it says, for the demand function Q equals D of P, 337 minus P, find the following elasticity. So here, the variable is P, and the one we just talked about in the book, it was X, and sometimes it will be X in our homework as well. So can we find the elasticity? So elasticity was defined as the opposite of X times D prime of X over D of X. So I need to find my pieces. Okay. So what is D prime of P? Well, I think for this one, it's just -1, right? That's 337 minus P, dP over, I'm sorry, D over dd over dP would just be -1. So that's not too bad. The variable in this is P, so we have minus, whoops, break that up. P, -1, and then the original. Now I can clean that up because we have minus. That's just P 337 minus P. Find the elasticity of the given price, stating whether the demand is elastic, inelastic, or has a unit elasticity. E of 90, I'm just going to plug it in. For this one, we want to write it as a fraction. That's important to note how it wants it. So 90/247. This is inelastic because it is positive. And they say in that book that it's inelastic if it's positive, elastic if it's negative. Find the values of P for which the total revenue is maximum. Okay, so for that, we want to maximize it. See the following values of P for which the total revenue is maximum. Assume that P dollars. Can't remember. I don't think it's the second derivative. Oh, that's where we said equal to. So I'm not a business guy, so I don't know this stuff. All right. E of x equals 1. Solve for x or solve for P in this. Okay. So that would be P 337 minus P equals 1. We can just solve. P equals 337 minus P. And P equals 337 minus P. 2P equals 337. P equals 337 divided by 2. P equals 168. 50, please round to the nearest cent. All right. So when the elasticity equals 1, this is the maximum. But really, for me, it's just an application. If you're a business person, you need to dive a little deeper. I want to show number 2 because I believe it's similar, but it has a different variable. This is how it's set up. For this one, we have d of x equals 600 over x. Okay, we want to find the elasticity. So we need to find d prime. All right, what is d prime? I'm going to rewrite this as 600 x to the negative first. That makes it really easy to find. So d prime of x then equals negative 600 x to the negative 2, negative 600 over x squared. Okay. So x times negative 600 over x squared all over the original function, 600 over x. Let's do some canceling. There's 600 over 600, which equals 1. But I had to use that formula that they give me. Okay, so that's in the book. That's the definition. Definition of elasticity. And I take the derivative, multiply it by the variable, and the negative variable divided by the original demand function. I just got 1. Okay, so what is E of 8? Well, it would still be 1. Now, of course, since the elasticity always equals 1, that's a unit. The 1 is the unit of real numbers. That's the unit of elasticity. But that's just an application of what we've been learning. It's kind of interesting, I guess. 3 and see if it brings anything. It brings along some interesting derivative. Okay, so we have d of p equals 299 minus p to the 1/2. Remember, square root could be rewritten as to the 1/2. Then d prime of p equals 1/2 299 minus p to the negative 1/2. If you like, you can rewrite that as 1 over 2 root 299 minus p. That's going to be negative. Elasticity, as defined in the book, prime of p, d of p. So let's build it. Negative p times our derivative, negative 1 over 2 root 299 minus p, all over the original. Here's where I wanted to bring up something about exponents. We have let 299 minus p equal u. If you let that equal u, what we have here is u to the negative 1/2 divided by u to the 1/2. So I argue that that would be u to the first. Well, actually negative 1. Little exponent. Just thought I'd bring it up. Why I'm going to simplify the value. We have a negative negative here. That becomes positive. We still have the 2. We have the p from here all over 299 minus p. That's where the square root is from the exponents. Now, we probably have different numbers, but the idea would be the same. I think would be relatively the same. From there, it wants me to find the elasticity at 85. So I wanted to plug in 85 into my newly found equation. Okay. And since this is positive, this is inelastic. Maybe the hardest thing was that part, okay?
I'm just asking questions.
Which part did I?
I don't know. I just got lost at something at the very beginning, so it's okay.
I can start over. I can start over. Let's try again. So I want to build this. So that's what I'm trying to build. That's my goal. P is the variable. So let's find d prime of p. So I'm told d of p equals this. I'm just going to rewrite it. One half makes it a lot easier. From there, I'm going to take the derivative. So the 1/2 comes down. The outside. And by chain rule, I need to take the derivative of the inside. I have a negative p So that's gonna give me a -1. From there, I'm just gonna rewrite it, clean it up for myself, but I'm not doing any calculus at this point. So that's my derivative. Okay, so from there, getting closer, -p times this, which is -1/2 root 299 minus p, all over the original. So that's it. That's the answer. I just need to clean that up the best I can. Need to clean it up the best I can. And this is what I was going on with the algebra part, which I noticed that these are the same, the 299, the 299. So let x equal 299 minus p. Okay, I'm just gonna swap variables because the square root, that's all too much. So what do I really have? I have -1/2 x to the 1/2 over x to the 1/2. That's what I have. These exponents will add. These exponents will add. So I think I have -1/2x. What was x? I gotta plug that back in. So now I have negative p over 299 minus p. And then p just becomes positive because negative. From there, I plug in the number that they asked me to. And since this is positive, this is inelastic. Elastic is negative. Now the last part is find the maximum. Well, the book will tell you that the maximum comes from when the elasticity equals 1. Okay. So you want to set that equal to 1. So find max. Let's set it equal to. Okay. How do you do that? E over 299 minus p equals 1. E equals 2 times 299 minus p. It's like 600, 590. E equals 598 minus 2p, 3p. Yep, that's just by setting the elasticity. A lot of algebra in between, but that's the idea. Some kind of sense.
Yeah.
There's a lot there. Any online questions? 4 is fairly simple, or similar, not simple. I think it's fairly similar. Yeah, it is fairly similar. Looks like I typed in the first part wrong. But again, if you want to find E of P, then you do this by going negative P, P prime of P over D of P. That's the formula coming straight from the book. Find your derivative. So that really is the same problem over again. So I'm going to move on because there's problems that are nothing like this at all. Let's see what 5 brings me. I think this will be okay if you take your time. Maybe read the hints. Again, find the elasticity. E of x equals negative x times d prime of x over d of x. That's, of course, where I'm finding elasticity comes from the formula, which comes from the book. So you want to find your d prime of x. Negative x times negative 14 all upon 794 minus 14x. Negative, negative makes positive. There you have it. So again, I'm not a business person. If you're going to school for business, I'm not just lightly suggesting, I'm heavily suggesting this is the week where you should take time to read that in the book. I'm only concerned about that. Great, John. But to me, it's just one more formula. But you're going to definitely need that. So I would have that on my cheat sheet as you've been building. That's 5. I think it will go. That makes sense. 6, I think, is similar. Yeah, find the elasticity. The only thing of interest is that we have to use quotient rule. Plugging in x equals 4, you can find the elasticity. And at $4 per plant, small increase, total increase. Okay, so it's pretty much the same. You just need to find E of x, which can be annoying as far as some of the algebra comes into play. But it is just one more example. Don't forget about quotient rule. That's extraordinarily important to us. So E prime of x be the derivative of the numerator, which is 5 times 20x plus 7 minus 20x plus, get ahead of myself, 5x plus 400 times the derivative of the denominator, which is 20. And then we want the denominator squared. I pray that we haven't lost quotient rule. Please don't forget about that. I think maybe the most annoying part when I was doing this was just simplifying as usual with the computer. 5 times 20 is 100. X. And 2 times 4 is 8, so that would be negative 1,000. And then 8,000 is 35. Again, just finding the derivative at this point. That's 5. Okay, so there's the derivative. Now I need to plug it into this equation. If x times this guy all over the original function. I did use another algebra trick. In case you're interested, let's not let x. Let u equal 20x plus 7. So if you do that, for instance, we have something like negative x times a number over u squared over, just say some other number over u. We have the squared, we have the u. That's going to cancel. There, we get 5x over 5x is 400, 20x is 7. So the way I was able to cancel out that squared was using the exponent rule from algebra skills. But it's like deeply embedded problem. Okay. So I hope that makes some sense. It looks like I made a sign. This was to be negative. So the negative makes sense. From there, I'm asked if x equals this number, plug it in. I would plug it in your scientific calculator, make it quicker. At $4 per plant, a small increase in price will cause the total revenue to increase. Saved a picture of it. Demand function, elasticity. It just takes a little bit of patience, and there is a little bit of algebra in there to simplify things. But hopefully, if you can peek at my example, peek at the example in the homework itself. That was problem 6. What's some notes on 11? I can't remember what I said. Let's look at 11. And we're about 20 till. So this is a exceptionally big homework, but I think we're on time. Before I move on, are there any questions, or should I wait a moment? Questions. So there's a elasticity chunk there. Any questions? Okay. That was 6. Let's take a look at 11. All right. Is that the first one of this type? Let's take a look at it. Let's take a look at 8, actually. This is a whole new type of derivative. a brand new title. You've never seen this before, unless you've taken this class before. Brand new. Implicitly. Okay, I did not understand this the first time I saw it, so hopefully I can explain it. I mean, when I was a student, not the first time I went to this problem, but hopefully I can explain it to where it makes sense. Y is a function of x when it says take the derivative implicitly. Okay, y is a function of x. What does that mean? That means that this is really 4x times y of x plus 1 equals 0. This is like a whole nother function. A whole nother function. And we've done that before, right? So we've done like the product rule. Okay. That's going on here. So don't think of y as a variable, think of it as a function. Okay, think of it as a function when they say implicitly. The first few are, I think this one is pretty easy. In fact, I think you can just solve for y and then take the derivative, but let's take it for real. See what happens. Okay. So this first part, I have 4xy plus 1. Let's take the derivative with respect to x. So think of f of x equals 4x. And then there's this g of x, which equals y. It's two different functions going on at the same time. So that means you have to do product rule. So the first point would be what? D over dx, 4xy plus 1 equals d over dx of 0. So I'm going to take the derivative of both sides. What does that mean? You get 4y, so I took with respect to x, so the x just goes away, it's just a 1. Plus 4x dy dx. Since y is a function of x, I'm taking the derivative with respect to x. Okay. So it's like product rule. As in f was a function of x, g was a function of x. Now y is a function of x. So when I take the derivative of it, I get this f part, and then you can think of y as like a g. So it's whatever the derivative of g is. We don't know. Then the derivative of 1 is just 0, so that goes to 0. And the derivative of 0 is just 0. Okay. So far, so good. Maybe. So that equals 0. Judging by facial expression, I don't think I'm doing a good job. 4xy plus 1 equals 0. Let's solve for y. We can also do it this way. 4xy equals negative 1. Solve for y. Y equals negative 1 over 4x. We could just take the derivative this way. So dy dx equals negative 1 4x to negative 1. So that's 1 4x to negative 2. Let's think about it. Let me say this again. I mean, we'll eventually have to get to that part. because they're gonna get so hard, we want the choice. So let's solve for y. Y x equals -1/4 x to the -2, 1/4 x squared. Solve for y, then take the derivative. Let's go to the next one and see what it brings. Suppose that x and y are related by the equation 5x squared minus 4y squared equals 2, and use the implicit differential to determine dy dx. Okay. But what I want to do is I want to take this d over dx, 5x squared minus 4y squared equals d over dx of 2. And of course, derivative of the constant is 0. So I don't have to worry too much about that. What's going on over here? So the derivative with respect to x of 5x squared would just be 10x. To deal with it. That's going to be the confusing thing. All right. So the next step, this is easy stuff, right? Break down the 2, 10x. Now what about this? Y here is a function. Y is a function of x. Y is a function of x. And it's squared. So that means I have to take the derivative of the outside and the derivative of the inside. So let's do that. Minus, so the 2 comes down, 8 y, right? But there's an x inside the y, because y is a function of x. So dy dx, think of chain rule. So I get a dy dx because there's some derivative of y. Does that make any sense? Kind of, sort of. Equals 0. Now I'm trying to solve for dy dx. So note, solve for dy dx. Okay, just think of it as a variable. So that means I get 10x equals 8y dy dx. I can divide both sides by 8y. dy dx equals 10x over 8y. And simplify. Five x over 8y. Y is a function of x. It's not a variable. It's a function of x. So when we take the derivative of it, we get dy dx. Take the derivative of the outside, and it leaves some on the inside. Once we find dy dx, we can solve for it as if it was a variable. That's the idea. Does that make some kind of sense? Okay. Let's look at another one. Build up to 11. Okay, let's look at my number 10 here. We have y to the 4th equals x to the ninth, I'm gonna take the derivative of both sides with respect to x. So d over dx, d over dx. Y is a function of x. What does that mean? When you take the derivative of it, you still have by chain rule the derivative of dy dx. So this becomes 4y to the third. That's like taking the derivative of the outside. And then the inside would be whatever dy dx is. That's the left-hand side. The right-hand side, we take the derivative just normally, 9x to the 8th. Exponent comes down, and it gets subtracted by 1. Now I solve for dy dx. So I will divide both sides by 4y cubed. So dy dx equals 9x cubed over 4y cubed. I would imagine the confusing thing is where on earth does this come from? The chain rule. So if you look back on when we learned about chain rule, sometimes we would sub it in, but we always knew what y was. Now we don't. Now we're solving for dy dx, but we don't know what y is. It's just in general. Makes it a little bit more confusing. And I was very confused. I still remember learning the implicit differentiation, and I didn't understand it at all when I was a student. So I hope that this will be good enough to get the idea. Let's look at 11. The computer will let me. Okay, let's look at this. The problem with this is that there's just so many steps. So it's not any different than the previous problem. It's just there's going to be more steps for this. That's why it's harder. Okay. The idea is the exact same. So I have this. I want to take d over dx of x cubed y plus y cubed x equals d over dx of 4. The good thing is the derivative of 4 is just 0. So automatically the right hand side goes to 0. So that's one less thing we have to worry about. What's going to come up is a bunch of product rule to deal with a lot of product rule. So we can take these individually. D over dx of x cubed y. What does that equal? So remember, y is a function of x. So it's kind of exactly like our product rule. So let's take the derivative of f here. So that would be 3x squared y plus the derivative of y. So that's x cubed dy dx. Switch colors here. What is the derivative of y cubed x? What is that? So the derivative of y cubed is going to be 3y squared, and then by chain rule, dy dx. And then we still have an x on the side. Plus the derivative of just that x, which gives me y cubed times 1. So those are the pieces. I put it all together, and I need to solve for dy dx. Okay, so let's do that. I hope, does the red show up okay? Is that easy to see? Is the red okay?
The red.
When I write in red, Is it easy to see?
Mhm.
Just need to switch colors. So let's add these together. I just put those together. Now we have it. Okay. That's the calculus part. Now comes the algebra part. And if you look at my notes, I actually do this for myself. I'm trying to solve for dy dx. Solve for dy dx. Is there like a faint version of this? There's a dy dx. There's a dy dx. So I need to get them together. I need to get those together. So I'm going to put those together on the left-hand side. X is 3y squared. I'm just going to move the x to the left here, just so it's a little bit easier to see. And there's some symmetry in the writing. I'm going to move, it's getting a little Christmassy now, but I'm going to move the other terms to the right-hand side. Because they don't have dy and dx. That one's going to go to the right. This one's going to go to the right. They don't have dy dx. I don't need them. I need them on the opposite side. So there they go. So that's negative 3x squared y minus y cubed. I'm trying to solve for dy dx. So I'm going to factor out dy dx. I'm going to factor it out like it was a variable. I'm going to factor it out. So if I do that, what do I get? I get dy dx. What do I leave behind? X cubed plus 3y squared x. I factored it out on the left-hand side. And I write what I left behind. Now I can divide both sides by what's in the parentheses. And that will solve for dy dx. So I'm dividing both sides by what's in the parentheses. There's dy dx. There's just a lot of steps. Each step is fairly simple, but there's a lot. And you have to kind of know what to do with each given moment. Is there any step you would like me to do again? Is there any one that would like me to do the whole problem again? It's kind of important to see this. It's an important concept. It doesn't go away in calculus. So is there anyone that would like me to do it again? Is there any portion you'd like me to talk about? We still have 15 minutes to talk. We're only going to go over 23. 24, yeah. How'd you do, Kelsey? Any questions about it?
I think get the right answer.
Okay. The only difference
Yeah.
between what I got here and the final answer was I factored in negative sign. So there was one step of simplification from here to here, but I think the computer was simple. I think
think,
that's the only step I didn't show.
no.
I didn't. Okay. Is there any part you want me to do again?
Because I accidentally wrote down your note.
Oh, yeah, that's gonna change the game. That'll change the game. Okay. I think now would be a good time to take our second break. But the only thing I'll mention is that for this, I believe this is actually easier than what we just did. You're gonna take this, go d over dx, y squared minus 2x cubed equals d over dx of 9. That of course goes to 0. It won't always, I mean, right hand side isn't always 0. It's just kind of being nice by doing that. So from there, we get 2y dy dx minus 6x squared equals 0. Solve for dy dx. So solve for dy dx, I get 2y dy dx equals 6x squared dy dx equals 6x squared over 2y. You can reduce 6 divided by 2 is 3 last time I checked. So that's 3x squared over y. And the only thing that's different between this problem and the previous problem is that they say find it at this given point, that given point. So I can plug those points in and find what I'm looking for. So I get 3 squared over, I'll just change the numbers that way. -5 for y, 2 for x. That. Okay. So I'm gonna take my other break. Let's take 5 minutes and do whatever we gotta do, get a drink, and we'll come back and we'll talk about more problems and some of the other ones are pretty heavy. We'll come right back. Okay. 5 minutes.
Yeah.
Guess it was kind of nice that they found out I could do that. Okay, just for participation points, could you write what state or country you're in? Writing in the chat box will give you some participation. What state, or if you're in a different country, what country? Okay, I'll briefly mention, I mean, these aren't too different than what we just talked about. Am I sharing the right screen? So, okay, so again, implicitly, what does that mean? You're taking the derivative with respect to x, but thank you for doing that. So you want to go d over dx, 5x squared minus 9y cubed equals d over dx of 53. Okay. The only thing that's going to change with this from the previous versions is we have some numbers to plug in. But I think this one, these are kind of easier. So the 2 comes down and you get 10x minus, I guess that would be 27y squared. And the derivative of any constant is 0, so that becomes 0. Whoa, you see my mistake. I forgot about the chain rule. So we have y squared, but you're also going to have dy dx equals 0 by chain. Since implicitly implies that y is a function of x. Very well. So by algebra, I can move and try to isolate. I'll divide both sides by the 27y squared. Find the dy dx for this problem is 10x over 27y squared. The only thing that's different about this one is that they give you some numbers to plug in. So I have 10, -5, 27, 2 squared. It's -5 over 54 after reducing. That's not too different than what we did before. We're just plugging in numbers. And I think in some ways it's easier. I think 14, 15, I think they're pretty much the same. I mean, they're different versions. It's, you know, it's relatively the same. So x squared, y squared equals 59. If you want to take the derivative, you just got to remember product rule. The constant goes to 0. So what do we have? We have 2x y squared plus x squared times 2y times dy dx equals 0. And the idea is that we're going to solve for dy dx. I can rearrange the terms, like this one, move it to the right-hand side. By both sides by x squared 2y. And we can do some simplification there. It goes to -1. goes to 1. So we have negative y over x. Simplifies a lot. Then the last step is just to plug in the numbers that they give you. For me, negative 1 over, whoops, I plugged in the wrong number. Excuse me. 7 over negative 1. So I just get 7. Are they getting easier? I hope with practice it would become clear what implicit meant. I mean, this is more of the same. More of the same. We just peek on. Let's go to 16 and see. It's pretty much the same thing, but we have to switch a variable here. So we're solving for dp dx. We're finding that this is implicit, which means that it's p of x. And remember, this could apply to our cost, revenue, profit function, that kind of thing. All right, so let's do it. D over dx, e to the 5th, plus p minus 4x equals d over dx, 55. But the derivative constant just goes to 0. So that's easy stuff. Oh, okie dokie. Now, we would have 5p to the 4th dp dx. That's that first term. Plus, and then this is just a single p, no coefficient, no exponent, just 1 dp dx. Now for the negative 4x, we're going to take that derivative just like we did second week of class. So that's exponent of 1 comes down, goes away. So that's just a negative 4. And we have 0 on the right hand side. Now, we want to solve for dp dx. So at this stage, we can treat it like a variable. Okay, we're solving for it. So I want to solve for dp dx. So I'm going to put them together, put everything else on the right hand side. And I'm going to factor it out, solve for it. Okay. So everything that has a dp dx, leave it as it is. I'm going to move the 4 to the right hand side. Now I can factor out this just like it's a variable, okay? So I'm going to factor that out. So factoring out dp dx. What did I leave behind? 5p to the 4th plus 1 equals 4. Now I'll divide both sides by what's in the parentheses. So I find dp dx equals 4 on 5p to the 4th plus 1. So that factoring step is important, and I can imagine a little trick. Good? Good? Okay, good. Let's peek at 17. I was hoping that if we looked at enough, those would be okay. I think 17 is going to be easy stuff. Let's do it. D over dx of xp to the 3rd equals d over dx of 7. That's going to go to 0. Okay, so we have product rule. So the derivative of the first function is just x, so that x goes to 1, we just get p to the third. Now, we leave the first function alone, and we take the derivative of the second. So we get 3p squared. By chain rule, we then get dp dx. And that equals 0. Okay, now again, name of the game is to solve for dp dx. So I'm going to move the p cubed to the right hand side. That way it's by itself, and then we can just divide and conquer. Okay. So I get 3xp squared times dp dx equals negative p cubed. Now I'll just divide both sides. That'll give me dp dx equals negative p cubed over 3xp squared. From there, we can just simplify. Implicit differentiation, is that okay now? That's good. That's a cornerstone of Calc 1. So we don't want to discount that. Next part is, these are the really annoying ones. So hopefully I can show you all the tricks, but it's just really like abusing algebra to try to solve these. There's no, I mean, I like them, but there's no new content really. It's just they're tricky. Look at what we're doing. Okay, so it says use logarithmic differentiation to differentiate the following function. So what does that mean? We're just finding the derivative. Just find the derivative, okay? There's no implicit anymore, just find the derivative. We've already have a technique to solve this, okay? We already have a technique to solve this. Well, a few techniques. We have product rule and chain rule. And we've already solved problems just like this in the homework. Okay? They're going to have us use logarithmic techniques to do this because some of the problems are so complicated that you pretty much have to use a technique. I mean, you don't have to, but you should. It makes it a lot easier. Okay, so you could just use product rule and chain rule, that's what I'm saying. Right? And there would be some where you could just use, yeah. So what am I saying? Maybe you do both, okay? Definitely know how to do both. If you're absolutely stuck, just do product rule. But let's learn the new stuff. So it's saying use logarithmic here, okay? Now what's that all about? What's the logarithmic thing? Remember that if you take the log of something like x cubed, that's 3 ln of x. That's the idea. So if you take derivative, or if you take the log of something or the natural log of something, the exponent just comes down. That's nothing to do with calculus, that's algebra. That's an algebra thing. Now, what about d over dx of something like this? The d over dx would be something like 3, because the exponent comes down, then what was the derivative of dx ln x? What's the derivative of the natural log? 1 over x. So this would be 3 over x. So that's algebra and calculus at the same time. How is that gonna help anything over here? Well, it helps with the exponents, it turns out, and it does kind of help. Some things it makes more complicated, but we'll get into that. So the first thing I'm gonna do is I'm gonna take the natural log of the entire function. I'm gonna do ln of f of x equals ln of x plus 7 cubed, 5x minus 4 to the 5th. So far, took the natural logarithm of the whole function. No calculus yet. From logarithmic rules, what does that mean? There's a couple things going on. So from log rules, remember the ln of a times b is the same thing as ln of a plus ln of b, the product rule of logs. And because it has exponents, the 3 would come down, the 5 would come down, or whatever your exponent is. So you have 3 ln of x plus 7 plus 5 ln 5x minus 4. So far, I haven't done any calculus. That's all just logs. Just taking the log. Then the log will go away at the end. That's the good trick. Now, from there, I'm going to take the derivative of both sides and see what happens. Okay, and what happens when you do that? So d over dx of ln f of x equals d over dx 3 ln x plus 7 plus 5 ln 5x minus 4. And we talked about over here, what is the derivative of ln of x? It's 1 over x. Okay. So what is this going to give me? On the right-hand side, what does that give me? So d over dx of ln of f of x, what does that give me? That's saying that this would be f prime of x over f of x. That's what the left-hand side gives me. F prime of x over f of x. Now it doesn't have a logarithm in it at all. On the left-hand side, it went away because we took the derivative. All right, what happens on this side? So you take the derivative of the first part of the first term, and you're going to get 3 over x plus 7. Thing in the parentheses. What about the second term? Well, it's going to be the same thing. Plus 5 over 5x minus 4. Now I want to solve for f prime. Right now I've solved for f prime over f. I need to solve for f prime. So I need to multiply both sides by the original function. I didn't write that. Times So what did I do? The first step was, take the natural logarithm of both sides. Well, why am I doing that? Because it told me to. Right? It's telling me that because it's saying it might be easier if you do it this way. So I take the natural logarithm of both sides. I play with the log rules. Then from there, I take the derivative of both sides, and then there's a consequence. Because the derivative of the natural log is just 1 over x, then on the left-hand side, I get f prime of x over the original f of x. On the right-hand side, it becomes really easy. I get 3 over the thing in the parentheses, or the exponent over the thing in the parentheses, exponent over the thing in the parentheses. Very easy to deal with. Okay. The only thing that's tricky is that in the end, I have to multiply by the original function. Okay. So then it gets a little hairy, but that's just algebra. And then the last step is to simplify. So now that we're here, we want to simplify. So we have x plus 7 here, 5x minus 4 in the denominator here. I don't know if you can see where I'm pointing the camera. But you have x plus 7 here, 5 minus 4 here. So we just need to play with the exponents. That's just algebra. The calculus is over. The logarithms are over. Okay, so we just need one more step to simplify this. But does this part, does getting here, is this okay? Are we happy at this point? Okay, the next step is just simplifying with algebra. That's the last step. Important, nonetheless. F prime of x. Okay, so I have x plus 7 to the third. When I multiply it against this part, I'm going to lose a piece. I'll lose a piece. So it's to the third, but it's over here, so that will become a 2. So x plus 7 squared, 5x minus 4 to the 5th times 3. So I really should have put that 3 up top, but I had to justify where it comes from. That's this term. Then multiply this against this. 5x minus 4 to the 5th. I have 5x minus 4 on the bottom. So this is going to lose an exponent. So it's 5, it'll become 4. So plus this 5, x plus 7 to the third, 5x minus 4 to the 4th. That's just simplifying using algebra. The other path would be to use product rule. But it can be challenging if the computer is saying use this technique and then you're supposed to simplify. Even if you had something that's equivalent, it might not understand. So I would suggest if it says use logarithmic techniques to use it. It's too challenging to try and do it without it. Any questions about what I did? Questions, comments, concerns? Does anyone want to see it again? There are a lot of steps. That's for sure. Question?
I have one question.
Yeah.
So your answer as 25 instead of 5 for the second.
Oh. Drop to 5 somewhere. Where did I drop it? That's a good question. I dropped to 5. remember. Uh, plus 7, 5x minus 4, x minus 7. Original. So there is a 5. I take the derivative. I took this derivative, it was a 1. So there should have been a 5 here, which makes this a 25, a 25. And this should have been 25. And this should have been 25. I apologize, I apologize, I apologize. So I dropped another number today. I'm glad you asked.
Sure. Cause I thought that's how that worked, but I just,
I'm happy to do the problem again, since I've made a mistake. Okay, so I dropped that 5. So when I took the derivative, I get a 5, I get an extra 5 here because of the derivative of the inside. So that becomes 25, 25. This is similar. Where are we at? If it's okay, I'm gonna skip to 23. Because logarithmic rules. So recall, there's a lot to recall. That if you have the logarithm of a over b, that you can write that is the difference, quotient rule of logarithms. So that's important to recall. We'll need that. That's gonna take the place of our quotient rule, which you could just take the quotient rule, by the way. So recall that. Recall that d over dx of natural logarithm of x equals 1 over x. We need that as well. And I think that would get us there. I guess I should say that x to the a is a natural logarithm of x. So the exponent comes down. There's a little cheat sheet for us. Okay, so let's do it. Natural log of f of x equals the natural log of 2 to the 12th over x minus 4 to the 8th. Just took the natural log of both sides. So from there, I can convert this to a subtraction. Natural log of x plus 2 to the 12th minus natural log of 4x minus 4 to the 8th. Next, I want to take the derivative, okay? So now, let's say, what is the derivative? D over dx, the natural log, f of x. to the left-hand side, recall that we're gonna get natural log of f of x, f prime of x. Let's switch colors, because it's gonna get way too much. This gives me f prime of x over f of x. Now, because of the logarithm, the 12 comes down. The derivative of the inside is 1. And the derivative of the natural log is going to be just what's in the parentheses in the denominator. That being said, I think this would be 12 x plus 2. That's the first term. Next, minus sign from the logarithm. The 8 comes down because of the logarithm. Derivative of the inside is a 4. Okay. 8 times 4 is 32. So I think we're going to get 32 upon 4x minus 4. Now that's the ratio of f prime over f of x. The next step is we have to multiply this by the original function. Switch colors. That implies that f prime of x equals the original function, x plus 2 for the 12th, 4x minus 4 to the 8th, times this new ratio that we found, 12 over x plus 2 minus 32 4x minus 4. Now comes the algebra simplification part. But that's the general idea. Any steps of this part? That part. So far, so good. Okay. Next part is to note we have x plus 2. So when I multiply this to this, I already have an x over 2, so that would go to 11. And this part is what it's gonna gain. So if you can imagine, when I do this, I'm going to have x plus 2 to the 12th over x plus 2. So that becomes 11. Exponent becomes 11. So we get 12 x plus 2 to the 11th over 4x minus 4 to the 8th. Now all I did was take this, multiply by the first term. Is that part okay? That's okay. Now do it to the other one. So if I multiply it by that, it doesn't have an x plus 2, so there's no reduction as far as that goes. So minus 32 x plus 2 to the 12th, that stays at 12, over, now this was 4x minus 4 to the 8th. This is 4x minus 4 to the 1st, so that's going to be a 9. I just add a 1. Just add a 1. Now, the total denominator would have to be 4x minus 4 to the 9th. So I need to do a little cross multiplication to make that happen. Or you can think, let me rephrase that. You don't have to do cross. This already has it. So we could multiply this by 4x minus 4 over 4x minus 4, and that would do it. That would do it. I have no room to do it, but that would do it. 12 x plus 2 to the 11th, 4x minus 4. I'm just going to write it up top. That's what we have room. use very much. Prime, that's equals 12x plus 2 to the 11th times a 4x minus 4 minus 32 x plus 2 to the 12th over 4x minus 4 to the 9th. All I'm trying to do is just get them over the same denominator. To do that, I need one of those to touch this. Then they would be over the same. This is 8, this is 9, so I just need one more. So I'm going to put one there, and that makes them over 9. Does that make sense? Again, it's just an algebra thing. There's no more calculus left, but it's a kind of, I guess, a pre-calculus thing. Okay, so that's the idea. So I'm just putting that one there so I get an extra one, and then there. And you can see, well, we would have gotten this with the quotient rule. Okay, we would have gotten with the quotient rule in the end anyway. Hopefully, that made some kind of sense. I think it's a simplification, more complicated. Questions, comments, concerns on that? Tricky problems. Okay, that was 19. I have 3 minutes. If I only have 3 minutes, what to do? Circle and cubes. One 36. We're given the volume. Radius is growing at a rate of 0.5 centimeter per week when the radius is 6.4 centimeters. How fast is the volume changing at that moment? What they're telling me here is the radius is growing. This is dr dt. This is radius is 6.4. I want to find the change in volume. So to do that, dv dt equals dv dr dt. The radius is the thing changing. The radius is the thing changing. They told me what dr dt is. They said it's this number. Okay, so that's easy. All right, what is dv dr? Well, if that's the only variable that changes, 4/3 pi times 3r squared. That's dv dr. 3's cancel. And then what's dr dt? They told me. They said it's this number. So with those restrictions, I have 4 pi. My r they gave me is 6.4 squared times dr dt is 1/2, 0.5. Don't forget to square it. You can use the pi button or 3.14, I'm sure. I use the pi button on my calculator. 257.4, and that would be centimeters cubed because it's a volume per week. So there's a few problems at the end like that where you have, where they give you the actual change in one variable to the other. You have to plug and shove. But those aren't very hard if you can follow along. It's not too bad. But you have to understand implicit differentiation. Okay, that's my time. I didn't get to all the problems I wanted to, so I'll probably have to make a video tomorrow about a few problems at least. Reach out, email me if you have any questions, concerns about specific problems. If you get stuck on one, you can always hit, it's my instructor. It's the best way to ask me a homework question. Is to do that, that way I can look at your version. Until then, I will see you next week, where we're gonna talk about the anti. Thank you for sticking around.